Um, I decided to change my plan a little from the announced plan. I thought that maybe since it seems that high temperature superconductivity in cuprates is not in the blood and bones of most of the audience, that I would expand upon the part where I just described the experimental situation and what sort of theoretical issues are posed by experiments in the cuprates. And so I'm going to do that actually over 1.5 or 2 lectures, not over 1 lecture. So today I'm going to start with some of the basic things that I think I sort of understand, and then my second lecture I'll get to things that are more confusing and more controversial. Well, everything is controversial. Just because I'm old and most of you are young, high temperature superconductivity has been around for a long time and has developed a bad reputation as a field. There's a good reason for that. In the first 150 years of the subject, it had a terrible sociology. We had a reputation for killing our young. Most of the old people here who are still working on the field were young at the time the field started and just barely escaped being killed. And then eventually some of that vitriol dissipated, but in general it was replaced by polite neglect. So it's to be hoped that now we're getting into a regime where we can talk to each other, we can disagree with each other fiercely, but without it becoming personal. So I'm hoping, and I had dinner last night with a few people from this conference in which, well, we think we drove everybody out of the restaurant because of our loud and enthusiastic debates about the subtleties of how to interpret experiments in the cuprates. But I think that's what we're hoping for in this field. So as I tell you things, feel free to object. I also want to say something positive about the field. It's been an extraordinarily productive study in terms of what's come out of it, partially in terms of understanding of cuprate high temperature superconductivity, but more generally in terms of the impact it's had on condensed matter physics. The number of experimental methods that have been developed or refined in order to address this problem is enormous. ARPAS is developed in large part in response to the challenges of this field. A lot of methods of STM, use of high magnetic fields to probe various properties of systems when you get to high enough fields to suppress high temperature superconductivity, all sorts of new optical methods. It's just been enormously productive in terms of stimulating experimental development in the field. And then similarly, in terms of theoretical developments, both in terms of techniques, the developments of new numerical methods for trying to handle these recalcitrant problems of strongly correlated electrons, and concepts such as spin liquids and all of these interesting topological states. They, in many senses, grew out of ideas that were developed in order to address the theory of high temperature superconductivity. I could go on, but I won't. Good. Right, so let me plunge in and let me discuss the phenomenology of the cuprates. And so to start with, let me draw for you a phase diagram. Now, normally you would think that would be non-controversial, but in the cuprates, everything's been studied so intensely that anything you say, there's a footnote. So let me first sketch something, and we'll discuss some of the footnotes on it in proportion to time. So phase diagram we're going to draw is temperature versus X, and X is something to do with the chemical structure of the particular material one's looking at, and it's what controls the concentration of, actually I would like to put this here where it stays, where I can refer to it. Where X controls the number of electrons per copper in the interesting copper oxide planes of the cuprate. So if N is the number of holes per copper, this is equal to 1 plus X. And so that's controlled chemically. And so this is where the phase diagram lives. And to begin with, there's an antiferromagnetic phase, and there's no footnotes on this. This is long-range antiferromagnetic order, and this marks a phase transition. And there is a superconducting dome, which I'm going to draw like this, and this has footnotes on it. There are many different members of the family of materials that we're dealing with, and in each of them the phase diagram has some differences and some uncertainties. The data that I'm going to invoke in the course of these lectures all come from three families primarily of cuprates, all of which are hole doped. So this pertains to doped holes. X is positive. The electron doped materials have some similarities and some differences. Those would be ones where X was negative. And so there are three families, and if you care and ask me specific questions, I can tell you which of these families the particular experiments or ideas I'm referring to come from. One is the so-called 1, 2, 3 family. 1, 2, 3 refers to the crystal structure. Yttrium, barium, copper oxide is the most studied member of this family. It's the cleanest in some sense of the materials, and a lot of experiments have been done on it. It has the problem that you don't really know what X is. Another family is the so-called 214 family, of which lanthanum, strontium, copper oxide is the most studied example. This is actually the only material where one really knows what X is. S is strontium. As you change the strontium content, all of the strontium goes in as an ion, so you know exactly what its charge is, so you know exactly what the concentration of holes is in the copper oxide plane. So in fact, every phase diagram that everybody's ever drawn is in some sense reference to a phase diagram of lanthanum, strontium, copper oxide. It's also the only material where one can really dope across this whole range of doping, and so actually have a phase diagram for the whole range of doping. And then something like that. What? Another C. The bismuth family, this is the material that has the best surfaces, and so all of the data that comes from surface-sensitive probes, such as angle-resolved photoemission and scanning tunneling microscopy, is primarily from BISCO. So, and all of these materials have their differences, and I'm going to, in large degree, overlook those differences and sort of merge things together in an impressionistic general phase diagram. Okay, so this is a superconducting phase, and it's in fact a D-wave superconducting phase, and this is a phase transition, and so although details of the shape may matter from material to material, again, this part of the phase diagram doesn't need a lot of caveats associated with it. There are a few other lines I want to draw. There's a line that goes something like this, and this is a spin glass transition. And, well, probably that's a real transition. Spin glasses are a little bit complicated in any case, but this is as good as any other spin glass. There's some spin freezing that occurs here. And then what else did I want to draw on this phase diagram? I wanted to draw a bunch of other things. Right, okay. So I wanted to draw a line that goes like this, which is called T star, and we'll worry about just what that means in a minute. But here we have a bad metal regime, and I understand there's been a lot of discussion of the physics of bad metals. That's in a sense the normal state out of which superconductivity develops, at least near the optimal value of doping. So here, optimal doping is the value of doping at which Tc is highest. That's the definition of optimal doping. But there's also some thought that there's some extrapolated end of this T star line, which I'll call X star, and I will talk about those in proportion to time. Might as well mark down some critical values. There's a critical value of the doping at which antiferromagnetism goes away. There's a critical value of doping at which superconductivity goes away on either side. There's a critical value of doping at which spin order goes away. And then there's a doping somewhere here, which is called 1/8. Well, that's a joke, but not really. It's called 1/8 because there may be some commensurability associated with it. It may be associated really with 1/8, or it may be just that something happens around 1/8. So there's physics hidden in this name about whether this is really something that has to do with a commensurability effect at exactly an integer, a rational fraction doping, or whether it's something that occurs at, say, x equals 0.12 or something like that. And in this region, there are strong spin density wave fluctuations. In this region, there's strong charge density wave fluctuations. There's some even vaguer line that's drawn here where these things seem to onset, and at which maybe the system also tends to become pneumatic. And so the dashed lines are certainly, well, no. The dashed lines are not obviously phase transitions. So one of the things we'll discuss is whether any of them are phase transitions or not. So if they're and this is called the pseudo gap. if they're phase transitions, then we're going to have to ask a more precise question about what are the two phases. If they're crossovers, then they may be some change in the short-range correlations. And so that's one set of questions we're going to want to address, is what these dashed lines mean. But empirically, there's rather different behaviors of certain correlation functions here. So here, if you do neutron scattering, you see lots of low-energy magnetism. You see some substantial correlation length for the spin correlations, which means large compared to 1. Here you see you see nothing in terms of low energy magnetism, and you see there's generally a spin gap, which is substantial, and spin correlation lengths are never more than about 1 lattice constant, but you see something in the way of charge density wave correlations when you look at, say, X-ray diffraction. Nematic refers to whether the crystal point group symmetry is spontaneously broken or not. And pseudogap is called pseudogap because we don't really know what it means. So that's what pseudo means. And let's see. I'll give some conventional numbers. So this antiferromagnetic critical point occurs at about 2% doping. This spin freezing transition is rather material dependent, but maybe occurs at 9% doping. X minus occurs at 5% doping. X plus occurs at maybe 26% doping. 1/8 occurs at about 1/8. Optimal doping is something like 16%, and X star is conventionally taken to be 19%. Of course, there's no reason for these things to be universal. They probably vary from material to material. The fact that all of these things, or many of these things, look similar in many of the cuprates confirms our intuition that the basic physics has to do with the ubiquitous copper oxide planes and is not enormously sensitive to the rest of the crystal structure. Yeah. It does. That is to say, you see a sharp transition here in the antiferromagnetic state. So exactly what that means is a little bit complicated. For those people who like these sorts of things, you might say that's where replica symmetry breaking occurs, but I'm not sure I like that sort of thing. What you definitely see is that there are moments that are ordered, and then there are other moments that are somehow associated with the disorder, and at this point those moments order. But whether there's actually a sharp phase transition here or not is another thing that even in theory isn't clear to me, whether it is to some other people.
The question about that part was asked. Do you put also incommensurate magnetism on the phase diagram?
So that's what I called SDW here. So nobody has ever seen long-range SDW order. Okay, so now there are differences from material to material in how long range of spin density wave and charge density wave order you see. And also here I've drawn the one thing that's different between two families, YBCO and LSCO, is this interplay between charge density wave and spin density wave. So maybe I'll put that here as a note. In YBCO, as I've shown here, the SDW and CDW are distinct. That is to say, first place, the ordering vectors are mutually incommensurate with each other. And it seems that if you have one, you don't have the other. They seem to fight. In LSCO, both short-range SDW and short-range CDW order exist over this whole range of doping. They occur together, and they're mutually commensurate with each other. So, yeah. There's none what? No. So in BISCO, there is certainly short-range charge density wave order that's been seen now with a large variety of methods. I know you have another interpretation of it, but it occurs at the same ordering vector with the same strengths. It's enhanced in magnetic field in the same way, so it's clearly the same phenomenon. The SDW correlations look much more like YBCO than in, so that at least here, there's no substantial SDW correlations in BISCO as well. Yeah, so here, well, okay, good. Right. Okay, so I realized I skipped something I wanted to say. Let me just go back for a minute and say that. Okay, so here, this is a horribly complicated phase diagram. You might ask, why do we want to study a system that has such a horribly complicated phase diagram? So certainly, this horribly complicated phase diagram tells us that the physics is going to be very hard to understand. It means that somehow there are many different ordering tendencies, all of which are somehow comparable in strength to each other, that have some complicated interplay with each other. And that also means that if we try to solve any problem and we make some approximation, we're likely to get the wrong answer. If we're looking at a simple metal, as Andre emphasized, there's only one instability, which is superconductivity. So you've either got a metal or you've got a superconductor. Okay, you might get TC wrong, but you're not going to get the phase diagram wrong because there's nothing else in town. Here we've got a zillion of different phases, and I've really only just started. There are more phases that have been at least conjectured, and some of which have been seen. And that means that if that's part of the right physics, that it's going to make theoretical physics intrinsically hard. And so you might say, let's just say that this material is too complicated. This is like studying the physics of wood. And why don't we study something simpler? So let me again defend the idea of studying these materials. And so I think there are several interesting things. First place, it exhibits high temperature superconductivity, and I think that's intrinsically interesting. I know it's a number and it's not universal, but it's interesting. The second thing that may appeal to some of you more is that by far the cuprates are the best studied of all highly correlated materials. And so if you want to have experimental data, serious experimental data, to confront with theory, to ask whether you're really understanding things, this is the best place. And thirdly, maybe we need to start asking somewhat different questions. We maybe will admit that if we have many phases that are in close competition with each other, that we're not going to be able to answer the question for this particular compound at this particular temperature, which phase are we in? But maybe we can understand why so many phases are in close competition with each other. This is, I've given this a name. Sentil talked about how important it is to name things. So we've named this, but we don't understand it at all. But we've named this intertwined orders. So there's somehow a sense that when you tune your system somehow to highly correlated or materials that are going to find high temperature superconductivity, that you've automatically tuned many different orders that are somehow coming from the same microscopic physics with comparable scales. And, you know, just this morning, Andre showed us an example of how something like that might arise, where you have some RG process in which there is an array in which many couplings are diverging, and rather than converging towards a single critical fixed point corresponding to some stable phase, you can converge towards a ray in which many ordering tendencies at once are growing, and then some subtle thing happens at low temperature that chooses which of these orders occur. So that's at least the beginning of one possible way of understanding this. So maybe we can understand the phase diagram holistically, even if we can't understand detailed aspects of it. Yes?
Sorry, continue. Maybe you can mention what the critical temperature for superconductivity is and if you have no one
So in this material, it's, I don't know, something above 90 Kelvin, 93, 94 Kelvin. In this material, well, the tri-layer, it goes up to 110 Kelvin. And in this material, it goes up to 42 Kelvin. But if you apply strain or pressure, you can change those things. You know, it's on the order of 100 Kelvin. Are there other questions? Yes.
Because you mentioned Andre's lecture, so what is missing in that picture? So he sort of says, okay, there are different. You sort of summarize what.
Yeah, I'll actually get to that. I mean, there's a lot of things that are missing, but I think there's a lot that's captured in that. It's a weak coupling perspective, and it captures a lot of the spirit of the superconductivity, but there's a lot of things it doesn't capture, as we'll see shortly. Good. And then finally, there are serious proposals of the existence of interesting new phases of matter lurking in various places in this phase diagram. There's the possibility of some sort of FL star phase that I think Sentil mentioned yesterday, and there's the possibility of a pair density wave state that I may or may not get to, and there's various orbital loop current phases that have been suggested, and all of these things would be very interesting. Okay, good. Any questions? So I haven't yet started. You can see it's going to take me 2 lectures. Yes?
What was the motivation to look on this compound from the beginning? First, someone knew that there is such a complicated phase.
Good. That's a very good question. And so that we happen to know very well because the discoverer, Alex Mueller, has been very vocal about this. So he had the idea that perovskites, and these are perovskites, have particularly strong electron-phonon coupling. And in particular, for this structure, there is a Jahn-Teller distortion, which has, well, has to do with some subtle distortion of the copper oxide octahedra. And he had the idea that that Jahn-Teller coupling would produce particularly strong electron-phonon coupling, and that moreover, because it involved oxygen phonons, oxygen's relatively light, so the phonon frequency is very large. So the combination of a strong coupling and a large frequency, he thought, would lead to high temperature superconductivity. So he was looking for high temperature superconductivity here, but he was certainly looking for it in terms of electron-phonon coupling. So this wasn't the next topic I was going to cover, but since you brought it up, let's talk about that. So for much of my discussion, I'm going to pretend I can ignore electron-phonon coupling in these materials. Now, as a mechanism for superconductivity, I can't remember, was it you who mentioned that if, somebody mentioned that when serious people did ab initio calculations of the electron-phonon coupling and tried to estimate TC, that was you, was it?
But for pnictide.
Okay, but similarly for the cuprates, when people do serious calculations and try to calculate TC, they find that it's way too small. But more importantly, this is a D-wave superconductor. And a D-wave superconductor, for reasons that Andre has explained, really comes from repulsive, dominantly repulsive interactions. So although it's quite possible that phonons play a role in the physics, it can't be conventional, they can't be dominant. The repulsive interactions in the problem must be dominant, and of course that's confirmed as well by the prevalence of magnetism both in the phase diagram, but even when one looks far from the antiferromagnetically ordered state, if one looks locally, one sees that the local moments are still present, saying that the repulsive interactions at the microscopic level are really the dominant force in these materials. There's one other thing that I want to say about phonons. These materials, as you can see, have complicated expressions. I haven't put the numbers in, but if we could, say, put numbers in here, we see that there are 13 atoms per unit cell, which means there are 13 times 3, I mathematically challenged. There are 39 phonon modes, and there are 2 electron bands at the Fermi surface. So there is some version of a large N theory that one might imagine is applicable to the electron-phonon problem in these complicated materials, in the sense that the number of phonon modes is enormous compared to the number of electron modes. Okay, and with that, I'm going to abandon phonons. They'll come back at various times, but you know, Mueller is very unhappy with all the theoretical developments in the field, and he makes the very reasonable argument that there's been only one important theoretical prediction made, which is his prediction that these materials would be high-temperature superconductors, and that one shouldn't discount his theory too trivially, given its one enormous success. Okay, and with that, I will ignore it. Yeah?
The classes are always sort of a failure of equilibrium thermodynamics.
No, this is glass in the sense of spin glass, so it's, I mean, yes, it's quenched, there's quenched disorder, but the idea here, this is a phase in which you have thermal equilibrium of spins with some randomness in the couplings. And the randomness in the couplings is quenched. So that has some degrees of freedom that are out of equilibrium, but that's normal in solids. The atoms don't move around below some temperature. Okay, good. I forgot when I started. 10 past? Yeah, okay, good. Yeah. Okay, yeah, so let's see. I've talked about phonons. I've talked about structure. Structure does matter in some ways. I'm going to ignore that for the most part, but again, if you ask me questions about particular materials, details of the crystal structure will come in. And I might even end up telling you about the high temperature tetragonal and the low temperature tetragonal and the low temperature less orthorhombic and so on, all sorts of complicated phases, so beware. And then finally, I want to mention that, I mean, the spin glass shows this explicitly, but, you know, people have spent the last 30 years working on these crystals. These crystals are the purest, most crystalline materials that people can make, but they still do have a finite amount of quench disorder in it. And somehow in our minds, what we're interested in is what would be the physics of these materials in the ideal limit of zero disorder. But experiments all take place at finite disorder, and we have to take disorder into account when interpreting experiments. Just while I'm still drawing phase diagrams, I want to draw one more, which is what happens if we get rid of superconductivity. And so the way we get rid of superconductivity is by turning on high magnetic fields. So let's look at T equals 0. And here's magnetic field, and here's X. And even the highest magnetic fields we can reach still have energy scales that are small compared to characteristic electronic scales. So although I'm going to talk about high magnetic fields, they're high, they're the highest magnetic fields anybody's done experiments in, they're very impressive, but they're still small compared to electronic scales, and therefore, in general, their effect on electronic states are very weak. And the one exception to that is superconductivity. So superconductivity, of course, couples very strongly to magnetic fields, and above some critical field is suppressed. And so the idea here was, let's turn on a high magnetic field, high enough to suppress superconductivity, but at least we'll imagine in our minds that other than killing superconductivity, it's not doing a lot. And so it's giving us some idea of what the phase diagram would be with superconductivity turned off. Now, that's of course a lie. It's telling us what the phase diagram is with magnetic field high enough that it's killed superconductivity. The idea of superconductivity turned off is a mean field notion. It's something we use as a sort of a colloquial way of understanding, but one shouldn't get too carried away with it. Yeah?
So what are the typical scales of HC2 in these materials near optimal doping? I thought they were like really large.
They are. Well, okay, let's see. Here's X star. Here's X optimal. Here's 1/8. Here's XS. And so HC2 has been mapped out. So it actually, I don't have my, this isn't quite right. They have it more or less to optimal doping, but it's still shooting up by extrapolating at around X star. It probably goes up to something like 150 Tesla, maybe even more. That's not a measured number. So there is an interesting two peaks, and presumably it also comes down like this, although there's not a lot of data there. So there's a two-peaked structure to the critical magnetic field, and different people look at this and see two different things in it. One thing people see is, HC is peaked near these 2 points. That's these 2 points. Maybe these are somehow quantum, well, this one at least is a quantum critical point, but maybe somehow HC is enhanced in the neighborhood, and this maybe is the critical point that marks the end of the pseudo gap or something like that, and that therefore maybe HC is maximized in the neighborhood of these two quantum critical points. The other thing is that it turns out that charge density wave order is anomalously stronger near 1/8 doping, and that maybe what's going on here is there's some sort of more simple dome-shaped HC, but then there's an anomalous suppression of HC due to competition with another phase at 1/8 doping. And there's evidence in favor of both of those propositions. So there's another line that we can now draw here, like this. And so this is HC2. And HC2 is one of the most controversial symbols in this field. But what I mean by HC2 here is sharply defined. This marks the point of the resistive transition. So at low temperature and for H less than HC2, the system has zero resistance, and for H bigger than HC2, it has non-zero resistance. Now, there's also a notion of some sort of mean field HC2 that people bandy about a lot and they fight over a lot, that being the field at which local superconductivity is destroyed. That's not a particularly well-defined notion, and so I think part of the reason there's so much fight about it is that it's a fight over something that doesn't have a sharp definition. It depends on how you measure it. One thing that is a little bit disturbing is that in this regime here, which is an important regime for experiments, although the system is in a resistive state, in fact, the system exhibits quantum oscillations. So in this whole regime, the system exhibits quantum oscillations which are very clear features of a metallic state with Fermi liquid-like elementary excitations, in this case corresponding to an electron pocket. So this is not only a metal, I'll get to you in 1 second, not only a metal in the sense that it's resistive, but it's a metal in the very precise sense that it has a Fermi surface and it exhibits sharp quantum oscillations. Nonetheless, in this regime, one also sees magnetic hysteresis, which is another one of the signature features of a superconducting state. The quantum oscillations are seen, actually, sometimes they're seen, in some features they're seen down to as low as this line, which I'm about to draw. I mean, not in resistance, but in magnetization. But this normal state does exhibit some features of superconductivity, some rather dramatic features of superconductivity. And I think the only way that one can understand that is if one imagines that these cleanest and best of all crystals in the universe are macroscopically inhomogeneous, and that small portions of the system that are nonetheless large compared to the penetration depth are still superconducting at these high fields. At least I don't know any other way of explaining that. That's an extremely unpopular explanation. And so this line here is associated with some transition in the charge density wave correlations that I will describe eventually. All right, so that's the phase diagram. We're going to discuss a lot of things about this. If you're a fan of quantum critical points, you've got a zoo of them here. There's here an antiferromagnetic insulator to spin glass insulator transition. There's a superconductor to insulator transition. There's a spin glass, metallic spin glass to, superconducting spin glass to superconductor transition. There's maybe a pseudo-gap quantum critical point, and there's a superconductor to metal transition. And that's even ignoring whether one wants to take seriously some of these other ordered phases that may occur there. At any rate, here, there's a superconductor to metal transition driven by a magnetic field and a non-charge density wave to charge density wave transition driven by a magnetic field. So there's a whole plethora of quantum critical phenomena.
Some of like LSC, isn't it also density wave transition?
Yeah. In the same sense, in the same sense as here, there's going to be some caveats on that, but in LSCO, as Subir says, where the charge and spin density wave are linked with each other, there is also a field-driven transition to spin density wave order. Yeah.
So how does one actually see this charge density wave transition, that it goes from some fluctuating order to some long range order? Is there a drastic change in the correlation length?
There's a drastic change. So these are things I'm going to discuss in my next lecture, but here, if you look at the onset of charge density wave here, it's vague. It's basically where a peak that you see in a diffraction experiment comes up above a background. There's no singular temperature dependence to the charge density wave correlations. They just sort of rise up. Here, there's something that looks an awful lot like a phase transition. So, first place, the charge density wave correlations here have some differences with the charge density wave correlations here. Here, the charge density wave correlations are unidirectional. And so there is a peak that comes up. It's a three-dimensionally ordered peak that comes up. It comes up with a field dependence that looks like the field dependence of an order parameter. There are also ultrasound experiments that detect a thermodynamic phase transition at the same value of the field. So I suspect that this isn't actually a phase transition on theoretical grounds, but on empirical grounds, this looks operationally like a sharp phase transition. So that's why I've drawn it as a sharp phase transition.
Why do you think it's not a phase transition on theoretical grounds?
Because, okay, so tell me what the two phases are. Okay, well, this phase is a superconductor without long-range charge density wave order, and this is a superconductor without long-range charge density wave order. Why do I say that? Well, first place, they measure a finite charge density wave correlation length, but second place, we have a general theorem based on the Imry-Ma argument that we can't have a long-range order of an incommensurate density wave, of any breaking of a continuous symmetry. So the fact that there's no charge density wave order here, there's no long-range charge density wave order, is both empirically understood and theoretically understood. Now, there still could be a phase transition here there could be a nematic phase transition. As I said, down here, the charge density wave is more or less of equal strength in the two different crystallographic directions. Here, on the other hand, the charge density wave is only in one direction. So this could be a spontaneous nematic transition with the charge density wave correlations going along for the ride. That's actually what I think is going on there. However, what?
That's rounded by something else.
So that's rounded by, in YBCO where it's seen, it's rounded by the fact that the crystal already breaks that symmetry. So this, again, can't be a sharp phase transition on those grounds. And even if it wasn't, it's an Ising order parameter, so it is allowed to have a thermodynamic phase transition in 3 dimensions, which this is. However, we also know that you can never see the random field Ising transition because you fall out of equilibrium inevitably before you reach the transition. So on any transition that you want to propose that's sharp here, I can tell you why, in principle, it's not going to happen. But I think it happens close enough to a transition that as far as the empirical statements are concerned, it behaves like a phase transition. And so that's exciting. That's new. That's a new piece of data, a new piece of evidence. I think that what's being seen here is a nematic transition. But at any rate, what's being seen there is something that's operationally a phase transition. Yes?
About this comment on the discrepancy in X, so is it just a scaling, or the question, what is the problem there? Is it just scaling of like how much you're actually changing one X, or is it you don't even know if you're changing one variable as you're changing something?
Right, okay, good. So let's take YBCO as an example. So YBCO, what you actually vary is the oxygen content. Now, as you change the oxygen content, oxygen likes to go in as oxygen double minus. So if you just did some chemists counting, you would be able to figure out how much doping you get for each oxygen you put in. But they're inequivalent layers here, so you don't know whether those extra holes go into the copper oxide layer, which is where the business occurs, or stay in the chain layer. Worse than that, we have evidence that as you change the degree of oxygen ordering, keeping the oxygen content the same, you actually change the effective doping. So you really have no a priori way of knowing exactly what the whole concentration is in the copper oxide planes. So the way you figure out what the doping is in YBCO or BISCO is you measure something, and for some reason that I don't understand, what people tend to measure is the thermal power at high temperature, and you compare it to what you see in LSCO. And if it looks the same, you say those are at the same doping concentration. Okay? There are some slightly better ways of doing things. As you dope the copper oxide plane, the apical oxygens, which are negatively charged, are electrostatically attracted to it. So it's a reasonable supposition that the distance to the apical oxygen is a linear function of the doping. And so then if you have two doping concentrations you know, which you probably don't, but you can at least guess, then under the assumption of a linear deformation, you can use that to measure the whole concentration. But anything you do involves some sort of argument and some sort of hopeful thinking. Yeah?
What about the Luttinger count?
What? Yeah, so the Luttinger count for these quantum oscillations has nothing whatsoever to do with the Luttinger count here.
Like Arcus,
So in ARPUS is very difficult to do in YBCO, and in particular the doping concentration at the surface has nothing to do with the doping concentration in the bulk. In BISCO, you can use the volume of the Fermi surface to make an estimate of the doping concentration, but the Fermi surface isn't very sharply defined. At low temperatures, it's pseudo-gapped. At high temperatures, the features are very broad. So you can get some estimate of the doping, but I wouldn't take it. I mean, any of these things involves some uncertainty. So, you know, my closest solid-state chemist friend, Ted Jabal, thinks that people are completely off on the doping. So I don't say that that's necessarily true, but it makes me worried that that some of this, you know, there's a lot of intellectual mode locking. It's really nice to imagine that all of these features occur at the same doping concentration in every material, and so people sort of wiggle their data to try to make them overlap as much as possible.
So the question was about the Luttinger count at very large doping of a large Fermi surface versus Luttinger count.
No, I think he was asking about Luttinger count as a way of measuring the whole concentration. Am I right?
Yes.
Yeah, okay. Good. All right, fine. So I've now presented a picture. I haven't told you I haven't focused on any sharp physical questions. So what I want to do is start easily. That is to say, I'm going to first tell you about the piece of this physics that I think we understand completely, or at least understand completely at the level I want to understand things. And that's what occurs at x equals 0. So at x equals 0, and there are many people, of course, that contributed to this understanding, but you know, I think the sort of seminal paper is by Chakravarti, Halperin, and Nelson in 1988. So let me tell you some things about the system at x equals 0. So in particular, okay, so what one sees, first place, is that there's a large gap in the spectrum. That is to say, there's a gap to charged excitations in the system, which is something like 2 eV. Now, the Néel temperature is something like 300 Kelvin, which is 0.03 eV. And J, the antiferromagnetic exchange, which I'll talk about in a minute, is something like 0.1 eV. And what you notice is that these scales, the scale at which magnetic order develops or even starts to develop, are very small compared to this gap. Now, this gap is something you can't get out of band theory, because at x equals 0, there's 1 electron per unit cell. So the conventional solid-state physics way of understanding this would be, I'd look at 0 temperature, where this system forms a Néel ground state. The Néel ground state doubles the unit cell, so now there are 2 electrons per unit cell, and therefore the system can be an insulator and have a gap. This description of the physics is clearly completely wrong. The gap has nothing to do with magnetic order. It's, if you want a pseudo gap, it's a gap that you might have wanted to explain by antiferromagnetic order, but then it exists without that antiferromagnetic order, although at low temperature it turns out that you do antiferromagnetically order. So at least for this, we clearly want to take a strong coupling approach to the system. We want to imagine notionally that we think about this system having a very large U on each site. Then at temperatures below the gap, we can think of this as being a spin-a-half Heisenberg antiferromagnet, and J is some antiferromagnetic exchange between nearest neighbor spins, which we might think is something like 4t squared over u. Now, if you think about this too microscopically, there is actually a slight problem with this. It gives you, if j is a tenth, it turns out the characteristic hopping is something like 2/10 of an EV. And so it means that t over j is something like like 2, which means that u is something like the bandwidth. So really, if you track back, you would conclude that the actual problem is an intermediate coupling problem. But in order to understand the magnetism, whatever the microscopic values of parameters, the right way to think about it is from the strong coupling perspective, where the gap simply has to do with the fact that you can't move charge around without putting 2 electrons on a site. It's a pseudo gap in the sense that it's a gap that's not directly associated with the development of any broken symmetry. And then what Chakravarty, Halpern, and Nelson argued was that if we're in a regime where the ground state is antiferromagnetically ordered, then we can describe the system at finite temperatures in terms of a two-dimensional O3 nonlinear sigma model. For this, we can calculate what the correlation length is, for instance, and other correlations. So of this form, where rho s is the renormalized spin stiffness, one can imagine trying to calculate rho s from microscopics, say for the nearest neighbor spin s. There's some expansion. They did this to some order in 1 over s, and then plugged in s equals a half, and get something like 0.15 j. And then could fit the measured correlation lengths measured by neutron scattering as they grow over a large dynamic range from psi of the order of 1 up to psi of the order of 200 lattice constants. That's really impressive. You can do dynamic scaling to get a understanding of the spin structure factor, S of Q and omega. Now, there are subtleties that they missed that are interesting in the theory of quantum magnetism. There are Berry phase terms that are important if you try to drive this system through a quantum phase transition. But as far as the description of the ordered phase, this is very effective. Oh yeah, one other thing. Okay, so here, this is the two-dimensional theory. The two-dimensional theory, of course, doesn't order. You would like to understand the physics of the Néel temperature. The physics of the Néel temperature can also be understood very simply. The cuprates are very layered, so the coupling between nearest neighbors, nearest planes, is much smaller than the coupling in planes. In fact, the J between nearest neighbor planes is something like 10 to the minus 3 of the J within a plane. But it turns out that for lanthanum cuprate, nature has given us an even better situation because the planes are staggered. So one plane's like this, and the plane above it is offset by this, which means that if you have a Néel ordered state here, the effective field it puts on the next plane is 0 to leading order. And so the effective coupling is either to second neighbor plane or higher order spin couplings. And so the anisotropy, the effective J perpendicular, is something like 10 to the minus sixth times J. So this is really the most two-dimensional antiferromagnet you can imagine. So then you might wonder why Tc is so high. And so that's, again, something one can understand easily. Notionally, if you look at the two-dimensional system, as the correlation length grows, you can think of a block spin of size psi s, which couples coherently from plane to plane, so that the effective coupling is renormalized by a factor of the correlation length squared. We could do it a little more formally. We could treat the interplane couplings in mean field theory, in which case, rather than psi s squared here, this would be an appropriate staggered susceptibility. And then what we'll get is we'll get ordering when this three-dimensional coupling is on the order of the temperature. And so that's going to give us an expression for the Néel temperature. It's going to be something like 4 pi rho s divided by the log of J over J perpendicular. And so even though J over J perpendicular is 10 to the sixth, the log of 10 to the sixth is 14. And so J perpendicular comes out to be, I don't know, a third of J. Okay?
Nail temperature,
The Néel temperature, what did I say?
J perpendicular.
No, the Néel temperature comes out to be something like a third of J. So even though this thing's enormously anisotropic and two-dimensional systems can't order, even this enormously weak three-dimensional coupling produces a substantial Néel temperature. All right, so that's the undoped problem. That's, I think, really a solved problem. Is any questions before I go on? Yeah.
So this is only between the next nearest neighbors, nearest?
You can also generate higher order nearest neighbor couplings. You can generate terms that look like Si dot S, I don't know, call it S. These are neighbor J squared terms, which tend to lock the order as well. So those are both of the same order, so it doesn't matter. Yeah.
So I guess essentially you're saying that if you have order multi-dimensional systems,
Correct.
So,
But the thing that's striking is, this is a small, if I told you that this coupling is 1,000,000 times smaller than the couplings we're keeping, you would say, okay, until I get down to astronomically low temperatures, who cares? But all that comes in is the logarithm of this. So even though that's 10 to the minus 6, the logarithm of it is 1.
so even though technically you don't have any order, but you're saying it's okay to just start with theory to mean say, well, you actually have another term that is in this order.
Right.
But is there any issue with that in any context?
I don't know. What sort of issue are you thinking of?
I don't know, that you might get some answer that doesn't make sense.
I think the answer is no. This is a general thing that things tend to, when you get to critical points, things tend to find out what their actual dimensions are because they're exploring the physics at long distance, and so no matter how much you try to cheat them microscopically, they'll figure that out. You could ask the question whether I've got the right small term. You could also get a finite transition temperature by putting in a small Ising anisotropy, which also exists in this problem, and also will give you a Tc that's small in the logarithm, in 1 over the logarithm, And there was debate about that, and I wouldn't actually bet my life that this is the right answer. But if it isn't the right answer, it's the same expression where this is the Ising anisotropy. Again, because we have spin 1/2, because copper is light, the spin-orbit coupling is relatively weak. Because it's spin 1/2, there's no single-site anisotropy terms, so all we have is the Jelshinsky-Maria terms, and they're pretty good estimates of how big those are from looking at the low-temperature physics. So I think that people are converged on the fact that it's J perpendicular, but okay, that's a detail that I'm not going to worry about. Yeah.
In any case, the ordering is three-dimensional.
The ordering is three-dimensional. The peaks that are seen in neutron scattering are resolution limited. This is really long-range order as far as we can tell. Yeah.
Sorry, so isn't it true that when people develop theories, they usually develop a two-dimensional theory for cuprates?
Yeah, so that's what I've done here. Everything up to here was two-dimensional. The business end of everything I did was two-dimensional. This is the best case. I mean, we're going to use two-dimensional theories always, but we never have this big of anisotropies to justify it. So this does show you that, you have to know what you're doing. So yes, all of the interesting physics is two-dimensional, but there can be subtle ordering phenomena that depend on the fact that the system's three-dimensional.
Theoretical consistency. I mean, if one is dealing with two-dimensional theories, then we know from Wagner that at finite temperature you cannot break continuously.
Correct.
With short range. So how do these two-dimensional theories actually succeed to get all this ordering?
Yeah, right. So that's what I've just said. What the two-dimensional theory tells us is how the correlation length grows, and it grows until you hit this temperature, and at that point you cross over to 3 dimensions. Okay? So the only, this is simple. The only deep stuff is this. And, this is perfectly consistent with Merman-Wagner. Coleman, Hohenberg. Okay, good. So let me talk about superconductivity now, which is the other easy problem. Not as easy as this. Good. So, somebody asked me, why wasn't what Andre described simply the solution of this problem? And I'm going to actually describe the superconductivity from a weak coupling perspective, and I'm going to argue that we actually learn a lot from that. But let's just point out some things that we're not going to get from the weak coupling perspective. So first place, from a weak coupling perspective, unless we have some very special band structure, the only game in town is superconductivity. So all of this other stuff on this phase diagram is simply not there in weak coupling. Moreover, the normal state in weak coupling is simply a Fermi liquid. It's a very good Fermi liquid. In fact, in weak coupling, it's practically a Fermi gas. And so all of this bad metal and pseudogap stuff is simply not there in weak coupling. So there's an awful lot of things that are not there in weak coupling. Weak coupling is in some sense wrong. If we're going to use weak coupling, we're going to use weak coupling along with a religious belief in the power of adiabatic continuity. We're going to imagine that there's some weak coupling problem that lives out here, and we're going to solve superconductivity in this weak coupling limit, and then we're going to adiabatically connect to the real system, and all sorts of other stuff is going to happen, but we're still going to hope that our insights about the superconducting state apply. Okay, so that's the idea. And if we're anyway relying on adiabatic continuity, I'm going to be able to avoid all of the important and serious issues that Andre addressed in today's lecture. If I'm inventing a fiduciary problem to understand the superconductivity anyway, I might as well take it to be the Hubbard model with only short-range interactions and not have to worry about beating these long-range interactions through some funny renormalization. So that's my choice. That's what I'm going to do. I'm going to look at something that has the right band structure for the cuprates, and I'm going to turn on some short-range interaction. I'll turn on a Hubbard interaction, but if you want me to turn on something a little more complicated, it doesn't make a whole lot of difference. And then we can use perturbative RG and Kohn-Luttinger type ideas, and in principle, we can get an asymptotically exact expression for TC, for instance, which is of the form that Andre wrote down. It will be, W is the bandwidth, so it will be of this form. And these coefficients depend upon the band structure of the non-interacting system. And in fact, these first two coefficients in this asymptotic series can be computed exactly from a knowledge of the band structure. I don't think anybody knows how to calculate higher order terms in this. That would need to do some matching because that's involved, as Andre said, in getting the prefactor right. But at least the first two terms in this asymptotic series one can get. And so one sees that one's going to get superconductivity directly from repulsive interactions. One other problem with this, of course, is this is a small u over w expansion. So this is a theory of low temperature superconductivity. In fact, it's even worse than BCS. BCS is small, the TC is small in proportion to e to the minus 1 over your small parameter. This is small in proportion to e to the minus 1 over your small parameter squared. Okay, so it's a theory of astronomically low TCs. And we can get the form of the gap, which is also going to have a form and so we'll calculate the gap to leading order. And what you find is that for any band structure, anything like the cuprates, the gap you find is D wave.
What's W here?
Bandwidth. Yeah. You know, you can apply this, as Andre said, to other problems to sort of test whether this gives you anything good. And so for the iron-based superconductors, as Andre already explained, it naturally gives S plus minus. It can also give D wave, depending upon details of what you do. I think the final word isn't in on the iron pnictides, but my understanding is that most people think that for the most part it's S plus minus, but there's probably some D wave lurking around. So in that sense, it's a triumph of this adiabatic continuity. In strontium ruthenate, it gives you either P wave or D wave being very close to each other. Those are still the most likely candidates for strontium ruthenate. For the organics, it gives you a close degeneracy between a D wave-like and a P wave superconductor, and probably the right answer is that it's D wave-like. So this notion of adiabatic continuity does have some successes in accounting for the symmetries of the order parameters. Yes?
So if the order parameter is D wave, the system is not in fact gap, right? So
It's got.
So how do you do adiabatic stuff?
Yeah, so I mean adiabatic continuity in the thermodynamic sense. That is to say that there's no phase transition as I vary the parameters. Not adiabatic in the quantum mechanics sense of adiabatic transport. So it means I'm changing some parameter in the Hamiltonian and the system doesn't pass through a phase transition. So it means that the asymptotic properties that I've computed in my model are the same as the asymptotic properties at the end of the day. Yeah, good question. Okay. So from this weak coupling perspective, we can understand why the superconducting state is D-wave, perhaps. Now, what we don't understand from this is why it's dome-shaped. In fact, if I did this weak coupling approach with a cuprate band structure, I would get my largest TC at x equals 0, well, somewhere near x equals 0. So we don't understand why there's this dome shape. We don't understand why there's this funny depression here. And this depression, as you can see here, will become, in fact, a deep minimum in the presence of a magnetic field. There's a 1/8 anomaly in the TC curve. We don't have any understanding of that. But there's an even more important thing that we don't understand about the superconducting state, and that's the following. So there are really two new features that characterize the superconducting state. One is the gap, and I've just talked about that. And within any sort of BCS-like mean field theory, and certainly within the weak coupling theory here, what one finds is that TC is going to be equal to some number, typically around 1/2, times the gap magnitude. And that tells you something. That tells you, if suppose you have access to zero temperature experimental data in the superconducting state, and somebody asks you, please predict TC. So in most conventional superconductors, you can do that easily. You just measure the gap, and then you know that the sorts of fluctuations that destroy superconductivity are depairing fluctuations. So the gap scale is what determines TC. Now, there's another number that characterizes the superconducting state, which is the superfluid stiffness. There's a term in the effective free energy trying to write down something gauge invariant so I don't get killed, of this form. And the existence of a non-zero superfluid stiffness is one of the characteristics. In fact, in some ways, it's the most fundamental characteristic of the superconducting state. And so what one can see is, at least taken as a classical effective Hamiltonian, this superfluid stiffness is what governs the fluctuations in the phase of the superconducting order from one region of the sample to another. In 3 dimensions, kappa has units of energy per distance. So to make an energy out of this, let me call it T theta, I have to take kappa and multiply it by a distance, and the only reasonable distance in this problem is the superconducting coherence length. So that's some energy scale that characterizes classical phase fluctuations in a 3-dimensional superconductor. In a 2-dimensional superconductor, kappa has units of energy, and so it directly tells me about some temperature scale at which phase fluctuations by themselves would proliferate and destroy the superconducting state. Now, typically in clean three-dimensional superconductors, kappa is something on the order of the Fermi energy or bigger. It's enormous compared to Tc, and it's so big that it's totally irrelevant. What that means is that phase fluctuations are extraordinarily stiff. The moment pairs form, they condense, and so the only issue is whether we have pairs or not. And so that's part of the reason for the success of BCS theory. However, in the cuprates, kappa turns out to be, or T theta, turns out to be very comparable to Tc. And so that tells us immediately that the superconducting state is order 1 different from normal superconducting states. It tells us that phase fluctuations, classical phase fluctuations of the superconducting order parameter, are an order 1 effect. Yeah? Yeah, so it's easy to understand why it's so large in conventional superconductors. So if I have a conventional in any superconductor, I have the F sum rule. So the integral of the conductivity is Ne squared over m. In a clean superconductor, all of this weight collapses into the superconducting delta function. So kappa is Ne squared over m. Okay, that's all electronic energies that has nothing to do with the small scales of superconductivity. Now, in dirty superconductors, this can be reduced, but you start with it so big compared to Tc that you just never get anywhere near here. Now, in the cuprates, first place, to start with, the unit cell is big. So the electron density is sort of an order of magnitude smaller than in conventional superconductors. And then, for reasons that are deep, the only electrons that count, or the only holes that count, are the X, the doped holes, rather than the 1. So that's 2 orders of magnitude already that the superfluid stiffness is lower than that of a conventional superconductor. Add to that Tc is an order of magnitude higher, and you've got a 3 orders of magnitude shift just to start with before we start even negotiating. Okay. And so, well, okay, I got through half of today's lecture. Let me not rush. Let me pick up there tomorrow.